This video is going to cover three common calculations that we do in the chemical laboratory: percent composition, empirical formula, and molecular formula. It's really important that you write down each of the examples that I go through so that you can come to class ready to do some example problems together in class. So the first formula that we use is percent composition, and this is probably the easiest of the three that I'm going to cover because we use percentages all the time. Percent composition of a substance is found by taking the percent by mass of each element in a compound or molecule. Make sure you copy down this formula. Okay, the percent by mass is found by taking the mass of an element in 1 mole of the compound divided by the total molar mass of that compound. And you'll recall from class that we did those last time. We just add up how many moles of each atom multiplied by the molar mass and add all of those together. And then of course we want it as a percentage, so we're going to need to multiply that by 100. So let's do an example problem. Let's take the common ingredient in baking soda, or the main ingredient in baking soda, sodium bicarbonate. You can tell by the formula of sodium bicarbonate how many moles of each element we have. We have 1 mole of sodium, 1 mole of hydrogen, 1 mole of carbon, and 3 moles of oxygens. And we need to know that in order to calculate the molar mass of the compound, just like we did in class before. We take 1 mole of sodium multiplied by its molar mass to get how many grams of sodium are in the substance. And we continue on. 1 mole of hydrogen would weigh that much. 1 mole of carbon. We have 3 moles of oxygen. And just like in class, once we know how much each element is contributing to the total mass, we add up all of those to get the total molar mass of sodium bicarbonate, which in this case would be 84.01 grams per mole. For all of these problems, let's just go ahead and take our masses out to the 100th percentage, so we can, or 100th place, sorry, so that we can determine significant figures fairly easily. Once we know the total molar mass, we're going to use our new equation to find the percent composition of each element. Now, percentages are always calculated the same way regardless of what class you're in. Percentages are always the part over the whole multiplied by 100. So we're going to do the same thing in this class. Okay, we know that our sodium is contributing 22.99 grams. The total mass of the compound is 84.01 grams. Divide those two values, multiply by 100, and we get what percentage of our sample would have a mass, or is sodium, by mass. We continue doing this for hydrogen, for carbon, and because we have 3 moles of oxygen, it's actually contributing a little bit more of the mass. Okay, remember that there were 3 moles of oxygen atoms, which have a total mass of 48 grams, divided by the total molar mass. Then we get a higher percentage of oxygen. Now we can check these problems really easily because if we total up our percentages, it should be close to 100, give or take a little bit because of rounding issues. Now we need to know percent compositions in order to determine formula of a substance, because if we discover a new substance and we know what type of atoms it contains or what elements it contains, we'll have to figure out a way to come up with the correct formula. So we have 2 ways to do this, and they go in order. The first one is called empirical formula. The empirical formula is the smallest whole number mole ratio of an element in a substance. Now this empirical formula may or may not be the actual formula that we would put on a chemical label. Okay, we'll get to how we determine that in just a few minutes. Okay, so here are the steps, or here would be an example problem. You'll notice that an example problem contains percentages, so we use those percent compositions to help us determine the empirical formula of a substance. So let's say we have a sample, a new sample that we found in the lab, and it contains 40.05% sulfur and 59.95% oxygen. Now for all of these problems, I'm going to highlight this because this is really important. That's not highlighting. For all of these problems, we're going to assume that the total mass of the compound is 100 grams, because then that makes it really easy. If we have a sample that's 100 grams, then 40.05 grams would be sulfur and 59.95 grams would be oxygen. Okay, so here's how we go about doing this. The first thing we need to do is convert each mass of each element into moles. So, like I said, if we assume that we have a 100 gram sample, then 40.05 grams would be sulfur. Use sulfur's molar mass from the periodic table, and we find that our sample would contain 1.249 moles of sulfur. And we do the same for oxygen, and convert 59.95 grams of oxygen into moles, and we find that we have 3.747 moles of oxygen. Now if you go back to the definition of empirical formula, however, it says we need whole number mole ratios Obviously, these are not whole number mole ratios. And I picked this problem on purpose so that you can problem solve in the future on how to figure out the lowest whole number ratio. If you get mole answers that are like this, that are not whole numbers, then here's what you should do. Take the smallest one, 1.249, and divide both of your answers by that value. So we're going to divide both by 1.249 to find our lowest whole number ratio. Now obviously this one would give me 1 mole of sulfur. If I take my calculator and do 3.747 divided by 1.249, I actually get a nice whole number. I get 3 moles of sulfur. So I've converted these weird numbers into whole number ratios, and now what I can do is I can write the empirical formula for our sample. We can't name it yet because we don't know what it is, but I know that I have 1 sulfur for every 3 oxygens. And that's how we find empirical formula. You need the lowest whole number ratio of atoms in a substance. Now, how do we know what the real formula is? Well, that's something different called molecular formula. And again, the molecular formula tells us the exact amount of atoms in a substance. It may or may not be the empirical formula. However, it will be a multiple of the empirical formula. So if you look at the formula here in blue, you're going to need to copy this down. The way that we find the molecular formula is we would actually have to go into the laboratory, or someone would have to give us the data. Someone would analyze a sample, and they would find the experimental mass of the molecular formula. Then we would divide it by the mass of the empirical formula that we had already found. And when we divide those two numbers, we get some integer, some whole number integer n, and we're going to use this value, n, to multiply the subscripts in the empirical formula to give me the molecular formula, which is the actual formula of that substance that tells us how many atoms we actually have. That sounds kind of confusing, so let's do an example. All right. So let's take a common gas used in welding, acetylene gas. It has the empirical formula of CH. So someone went into the lab, and in an experiment, it was determined that the molar mass of acetylene is 26.04 grams. The empirical formula is 13.02 grams. That comes from adding up 1 carbon plus 1 hydrogen from the empirical formula. So how do we figure out the molecular formula of acetylene? Well, based on my formula up here, I take the experimental value of the molecular formula divided by the empirical value, and notice we get a nice whole number. This integer is going to be used to multiply my empirical formula subscripts. So my molecular formula of acetylene is actually C2H2. The empirical formula, the lowest whole number ratio, was CH. My actual amount of atoms is C2H2. So that means I have 2 moles of carbon atoms for every 2 moles of hydrogen atoms in a sample of acetylene gas. So we've done an example each of percent composition, empirical formula, molecular formula. All 3 of these are related. So if you need to go back and copy down one of the equations, please do that. But come to class prepared to do additional problems next time.